Look at a modern city at night, consuming billions of watts of electricity. It is easy to assume that all the alternating current flowing through those millions of wires is constantly performing work. But there is a hidden paradox in our electrical grid. Just because current is flowing doesn't mean it is actually powering anything. This animation of alternating current shows why. Unlike the steady, one-way push of a battery, AC voltage and current constantly reverse direction, oscillating back and forth in a smooth, continuous sine wave. But depending on what is plugged into the grid, these two waves do not always line up. Certain circuit components, like the heavy motors in industrial machines, delay the current. As the current wave shifts out of sync with the voltage wave, it creates a physical gap between their peaks. We call this gap the phase angle, denoted by the Greek letter phi. Because the waves are out of sync, there are fractions of a second where the voltage is positive, but the current is negative. When you multiply the two to find the power at that exact moment, the result is negative power. Because of this constant, out-of-sync oscillation between positive and negative output, merely measuring the total current flowing through an AC circuit does not tell you how much actual work is being accomplished. To find the true energy used, we average the power wave's fluctuations over a full cycle. This gives the formula for average power, P equals V times I multiplied by the cosine of the phase angle. That final term is the power factor. Because the cosine of an angle always falls between 0 and 1, this term acts as a percentage or efficiency rating for the entire circuit. This power factor determines how much of the grid's electricity is actually converted into useful energy, and how much simply circulates through the wires without performing work. We can see how different physical components alter this efficiency using a vector diagram. In case 1, a circuit with a pure resistor, like a space heater, keeps voltage and current perfectly aligned. This means the phase angle is 0. Mathematically, the cosine of 0 is 1. In this scenario, the circuit operates at 100% efficiency. Every drop of current is doing work. Now look at case 2, a circuit containing only an inductor or a capacitor. These components store and release energy, forcing the voltage and current to be exactly 90 degrees out of phase. The cosine of 90 degrees is 0. Plugging that into our equation, total power dissipated is 0. This creates wattless current. Electricity physically flows and takes up capacity, but absolutely no work is being done. Case 3 occurs in a series LCR circuit, containing an inductor, a capacitor, and a resistor, at a specific target frequency called resonance. At resonance, the opposing effects of the inductor and capacitor cancel each other out, bringing the phase angle back to 0. The specific physical components we place into a circuit are what determine whether the current performs work or becomes a useless, wattless ghost. Out in the real world, this ghost current creates a hidden cost for power companies. To deliver standard power to a city, they must push extra current through the grid to compensate for the phase shift caused by industrial loads. This extra current increases heat loss in the transmission lines, a process governed by the square of the current multiplied by the resistance. That energy is lost as heat before it ever reaches a consumer. To fix this, engineers use vector resolution to split total current and diagnose waste. The horizontal vector, I sub p, is the power component, in phase and representing useful work. The downward vector, I sub q, is the wattless ghost current, generating heat but 0 power. To eliminate this waste, engineers connect a capacitor in parallel to the grid. This capacitor generates its own leading wattless current, pointing in the exact opposite direction of the lagging ghost current. Because they are perfectly opposed, they cancel each other out. The phase angle disappears, and the power factor is restored to 1. By managing the geometry of alternating power and eliminating wattless current, engineers ensure the electrical grid operates efficiently without drawing unnecessary energy from the source.